Hi everyone. So in the last lesson, I did say I will go through before I start the new content about the planetary motion, learning about Kepler's laws and how to apply them. I did say I will go over graphical representation of the gravitational field strength. So as a very quick reminder, we know that the gravitational force can be calculated using this equation. And since gravitational field strength is the force per unit mass experienced by a body at that point in space, we combine the two equations and we came up with G equals to minus Gm over R squared. So now we need to look at graphical representations of this graph. So if I wanted to plot a graph that has G against R, so this G against this R, because it's a negative value for what G will give us in terms of distance being positive, then we will expect to get a graph that looks like this. So minus that value means that G will be negative and R will be the positive value. So if I had, if I consider the center, the distance here to be the center, so this is 0. This is from the center of a planet or a big mass, a spherical mass. So if I consider that point, then, and since the graph is G against R, then I would expect to get a graph which looks like this. Now, if this is basically the highest value of G on the graph here, as distance increases, so as you go further away from the center of the mass, then your value of G decreases, so you will expect it to get less. Remember the fact that this is, let's say this was for the Earth, this was minus 9.81. So at the surface of the Earth, from the center of the Earth basically, it will be negative 9.81. But as you go closer, further away from the center or the surface of the Earth, so this is at the surface, as you go further from the surface of the Earth, you get a lower value until you'll eventually reach a point where it will head to 0 gravitational field strength. But we said it's quite infinite, so the distance has to be very, very huge at infinity where it will reach 0. So this is one way of seeing the graph. Now what happens in between the center of the Earth and the surface? It will normally be a straight line. Or we could redraw this in a positive direction. And in that case, it will look a little bit different. It will look flipped over, but obviously you need to label the fact that it's we're talking about negative values. So it will look something like this. So this is from, so this is your G, this is your R. So it will look like a straight line till the surface of the Earth. So this is where it reaches the surface of the Earth. You know that the value of G at the surface of the Earth is 9.81 newtons per kilogram, or meters per second squared. And then what you see is, as you move away from the center, so this should be the radius of the Earth here, because as a surface, so this distance will be R here. Then the further you move from the Earth, your value of G, so gravitational field strength, decreases in a inversely squared proportionality relationship. So that's why the line is kind of like a parabola. So now, how can I make this line be straight instead of curved, so I can even analyze it? The easiest way of doing that is to draw G against R squared. So G versus R squared. It will still be a negative line if we don't label the fact that, for example, in this case, this line was minus G m over R squared. So I'm labeling the fact that I made it positive when it was supposed to be negative. Yeah, for a straight line, sorry, you have R squared against G. That will give you a straight line going through the origin because G is minus Gm over R squared. So if Y is equal to mx plus c is my straight line equation, in this expression there is no plus adding a y-intercept, so the y-intercept is 0. So my line should start from the origin and it should be a straight line, since if I compare my two equations, let me redo it nicer, sorry. I know I can be messy at times, but I will eventually improve. So I chose my y-axis to be G. My x-axis is R squared. Sorry, 1 over R squared, because the equation is 1 over R squared. So if I draw this graph now, I will have a straight line, and we said there's no y-intercept, so that is 0, because there is no part of the expression. So G is equal to minus Gm 1 over R squared. So that's your gradient. Sorry, that's your x-axis. This is your y-axis. Didn't mean to do that. Y-axis. X-axis. That leaves you with this value being m, your gradient. So if I use the biggest triangle possible to find the gradient, and you have to use the biggest triangle possible and show that you've done that in the exam, otherwise you don't get many marks. And sometimes if you don't show that you use the graph, you won't get any marks at all. So your gradient will be equal to Gm, and G is a constant, so you can figure out from a graph the mass of the object that caused the gravitational force, basically. Okay, so now I'm going to talk about quickly how the gravitational field strength changes due to objects interacting. So the gravitational forces of two objects in space interact together and cancel each other out. So don't forget, gravitational field strength is a vector quantity, so it can be cancelled out by the gravitational field strength of another planet. What you see here is the Earth. If you consider yourselves being this astronaut, and then this is, let's say, the Moon on the other end. Now, if I were to look at the gravitational field strength and how it changes from gravitational field strength with distance from the surface of the Earth to the surface of the Moon, we'll have to consider the effects of each one of them on the person. So to begin with, if you're on the surface of the Earth, you will have gravitational field strength of 9.81 newtons per kilogram, and that should be at the radius of the Earth, obviously. So that should be the radius of the Earth. So I'll put a point there. Now, as the person's as the person is moving further away from the Earth, we would expect the gravitational field strength to decrease. Now, just to make sure that you understand this, the man will experience, the astronaut will experience, a woman or a man, will experience a lower gravitational field strength from the Earth. But as he's moving closer and closer to the Moon, then the gravitational field strength from the Moon will start increasing. Obviously, the Moon is much smaller than the Earth, so the gravitational field strength of the Moon is smaller and has less effect than the Earth would have. But as you get closer and closer to it, the gravitational field strength of the Moon and the Earth will end up cancelling each other at this point. So it will be closer to the moon. So instead of going to infinity, the gravitational field strength of the moon and the Earth will end up cancelling at around a point close to the moon. So you will expect the astronaut to... Oh, we're stuck together now. So you would expect the gravitational field strength around point B to be 0, so closer to the moon than to the Earth, because the gravitational field strength of the Earth is bigger than the gravitational field strength of the moon. So in their vector quantities, you know how to add vector quantities together and subtract them. So if you find the gravitational field strength of the Earth at this point and the moon at this point, they will cancel each other out and they will reach 0. But obviously, after point B, the astronaut will experience gravitational field strength of the moon as it moves closer to it. And we know that at the surface of the moon, G is equal to 1.6 newtons per kilogram. So it will look like this. Because we defined our position to be positive displacement from the center of the Earth, then obviously if it goes on the surface of the moon, G turns into positive. It will be in the opposite direction to what we were getting it from. So yeah, this is the graphical analysis of it. I hope that makes sense. If not, please do ask me questions in class or even in the comments below section. So today we will be having a look at Kepler's... Oh, sorry about that. We'll be having a look at Kepler's 3 laws. The centripetal force on a planet provided by the gravitational force between it and the sun. In the example I gave you with the astronaut, we kind of ignored the gravitational field strength of the sun. Sometimes it's useful because if it's closer to us, it doesn't have such a big effect, so we can ignore it. Then we will come across this equation and how to derive it is very, very important. It says it here as well in the comments that you need to derive it from the first principles. We're going to use Kepler's third law relationship to apply to to satellites and other things in our solar system. And we're also going to look at geostationary orbit and its uses in terms of satellites. So before we see his laws, Kepler's laws, it's a good point to mention that Kepler didn't have any knowledge about gravitational fields. All of his laws were based purely on observation. They actually helped other scientists come up with certain laws, especially Newton's law of gravitation. So I will be going through his laws and we'll see how we can apply them. In his first law, he said that planet's orbit is an ellipse with the sun at one of the two foci. So this is a planet going around in an elliptical path, an elliptical orbit around the sun based on one of the foci. So these are the two foci. And the sun is basically the center of one of the foci. So that was his first law. It's quite straightforward and simple. For those of you who do maths and you have seen elliptical shapes, they always have two foci, but you don't need to know much more in depth about it here. You just need to know that what Kepler's law says, that planets orbit an elliptical, they follow an elliptical orbit around the sun, being at one of the foci, basically. For our course, we won't be analyzing elliptical orbits, hence why it was very important to look at circular motion to be able to understand this chapter. So this chapter is quite closely linked to chapter 16, circular motion, where we will approximate the elliptical orbits to be circular orbits, which is quite a good approximation. Then we're going to look at the second law. So his second law, he's saying that a line joining the sun to a planet will sweep out equal areas in equal times. Meaning that if we have a planet here and we draw an imaginary line, so let me just draw an imaginary line between the sun and the planet. Now if the planet moves here and it takes, I don't know, let's say 100 days. So that's the equal time. So if it takes 100 days to move to that point, then, and I'll draw the line again between them, then the area swept between these points should be equal if I go to another point. So let's say the planet is here now. I'll draw another line joining the sun and that part together. And it took it 100 days to move to here. So to go there, I'll draw another line. So we call this area A and area B. Took both of these motions to 100 days. Then area of A should be equal to area of B. So yeah, basically says if you were to join the sun to planet in different parts of its journey, it will sweep out equal areas at equal times. So these two are quite forward and straight and simple. And then his third law. Actually, before I go to his third law, I just wanted to mention here that when a planet is closer to the sun, it tends to speed up. It's an important part. So this is a very important part of the motion of planets or comets that pass near the sun. So they're not constant because the closer they are, the more force they will experience, which speeds it up, so it accelerates it in a way. And one of the reasons we don't see comets very often, is because they have very elliptical orbits, and we can only see them when they're quite close to the sun, which pass very quickly. But then the further you go from the sun, there's less attraction they will have from the sun, and the lower the speeds that they move away from it. So yeah, I'll go to the third law now. So in his third law, he said that the square of the orbital period of a planet, so t squared, is directly proportional to the cube of its average distance, so r cubed, from the sun. So r being from the center to the planet, so r, and it's the average distance, meaning that you're kind of taking the radius of that motion, especially since we're not going to be using elliptical orbits. We're going to be approximating it to be a circular path, which is quite good modeling, because there's not much difference. There is a difference, but not that much that will affect our values extremely. So in other words, t squared is a constant times r cubed. Just to remind you once again, Kepler only done this through observation. So at the time, people just tended to use it until it was later on explained. This is an important rule because we're going to be using this quite a bit, but you do need to know all of them. They usually get tested in exams, especially since it's got to do with planetary motion, and it can link to other topics as well. So from Kepler's law, we saw third law. He said that t squared is directly proportional to the distance between the sun and the planet. It's directly proportional to the distance from the sun to another planet cubed. So we need to come up with an equation that fully links the period of a planet to go around the sun to the distance from the sun to the planet. We have already seen in circular motion that an object moving around a circular path has to have a centripetal force acting on it. Now, if we assume that this is the sun, okay, and that's the Earth, and this is the circular orbit around the sun. I know it's not a perfect circle, but you get the idea. Use a little bit of imagination. So if I assume that that's the orbit, now what forces are acting on the Earth? There's only one force acting on the Earth, and that's the gravitational attraction to the sun. So that should be my centripetal force. So my gravitational force acting on Earth should be equal to the centripetal force. We know that centripetal force can be calculated using mv squared over r or m omega squared r. You do need to be aware and know that this is the derivation of the equation that we're going to come out to. So you need to be very, very careful not to forget this. So before I continue, once again, you do need to know that the centripetal force acting on any planet is the gravitational attraction they have to the sun. And that's the only force, basically. So the centripetal force is provided by the gravitational force between the planet and the sun. So I can equate them. So centripetal force on the planet should be equal to the gravitational force on the planet. And we know that mv squared over r is equal to minus gm over r squared. We can simplify here, so the m and m can go, so we have v squared is equal to minus gm. I multiply both sides by r, which will mean this and that cancel, so v squared is equal to minus gm over r. Now this is one of the equations I can use to even calculate the speed, but we are interested in an expression that links period and radius together, so the distance from the sun. We know already that v can be re-expressed as v is equal to omega r, where omega is 2 pi over t. So I will place that in there. It will be omega squared, so that will be omega squared r squared minus gm over r. I will rearrange this equation, so that will be 2 pi, I just substituted 2 pi over t squared is equal to minus gm over r cubed, because I divided both sides by r squared. And we have 4 pi squared over t squared is equal to minus gm over r cubed. So I already have my expression here. I'm linking t and r together. I just want to rearrange them, make it look a bit prettier. So we'll flip both sides upside down. And make it look better from here on. So that will be t squared is equal to 4 pi squared r cubed over gm. So minus this expression. We can ignore the negative sign here because we're equating the forces, so I'll just ignore the negative sign because we don't really need it in terms of what direction it's in. So we come up with our expression for that links, we come up with an expression that links period and distance from the Sun, which is Kepler's third law. So the constant that Kepler figured out was this value. Obviously, that value varies for different mass planets only. And we use the forces that are acting on the planet to come up to this equation. So that's basically the proof and derivation you need to know. Alternatively, you could have used, instead of mv squared over r, you could have used m omega squared r is equal to minus gm m over r squared. That would have led you straight away to, if you divided both sides by r, that would have been, sorry, let me just get rid of m's from there. Omega squared is equal to minus gm over r cubed. And you know that omega is 2 pi over t, so that would be 2 pi over t squared is equal to minus gm over r cubed. Forget about the minus, keep doing that. And obviously you rearrange it and you'll still get up to this point. Okay, so what would I expect to get if I plotted t squared against r cubed? We look at the equation. T squared is equal to 4 pi over gm, 4 pi squared times r cubed. If that's my y and this is my x, I know that y is equal to mx plus c. I don't have a y-intercept, so I have my y, I have my x. I don't have a y-intercept because there's no plus sign there, so that's to start from 0. And that means that it leaves me with my gradient, which should be equal to this value. So if I draw a straight line through the origin, my gradient should be equal to 4 pi squared over gm. So don't forget about the mathematical analysis of these values. And never miss out, like for example, if here it said times 10 to the 5 or something like that, don't forget to include it in your calculation of the gradient when you get the change in y divided by the change in x. These are the common mistakes I always see in exams. Just a quick mention here as well. This law doesn't only apply to planets orbiting the sun. So even though we model the elliptical orbits to be circular orbits about it, and we make approximations, there's more objects that actually orbit each other, especially the ones that we place out in orbit around the Earth. So we place a lot of satellites, so we can approximate and use Kepler's laws in planetary motion of satellites, because satellites only have one force acting on them, which is a centripetal force, which is the gravitational force equals to the centripetal force. We also have things like moons as well orbiting, so natural satellites, and they're all very, very important in order of analyzing them using Kepler's laws. Okay, so far we have talked about Kepler's 3 laws. We have said that the centripetal force on a planet is provided by the gravitational force due to the attraction between the planet and the sun. We even used this, so it says you should be able to derive that equation. So we derived it using these principles, which is what it asked. We used the centripetal force is equal to that gravitational force, and we know that that gravitational force is minus gmm over r squared, and hence we derived it. So that's done. The relationship can be applied to systems other than our solar system. So it can be applied where we can approximate motion to be circular. And we need to have a look at geostationary orbits and how we can use geostationary orbits. Okay, so before I start about geostationary orbits and the geostationary satellites, I will talk in general about satellites. So we usually have satellites orbiting the Earth at all times, and they all follow Kepler's laws. So the centripetal force on each satellite is provided by the gravitational force between it and the Earth. So if I have, let me just add the Earth and the satellite around it. So if I wanted to place a satellite around the Earth, it has to have a specific reason, obviously, to be there. But I can use the idea that the satellite will only experience an attractive force towards the center of the Earth. So, and it will travel at a constant speed. So circular orbits, usually objects travel at a constant speed. It's just the direction of the velocity that changes, hence why it's accelerating. So yeah, this force is mv squared over r, which is equal to gm m over r squared. We already done this for Kepler's law before, but now we're going to have a look at it in a different view in terms of speed. So speed squared is equal to gm over r. Now if I square root both sides, the velocity of the satellite, or the speed of the satellite, is equal to the square root of gravitational constant times the mass of the Earth, divided by the distance between the center of the Earth to the satellite. So you can see that in this equation, the mass of satellite is not part of it. So that means the mass of satellite doesn't affect the speed of it, the satellite moving around it. So usually when they launch the satellites, their mass doesn't have any effect. It's just the given height that they need to be placed in that has an effect. Okay, so we're going to have a look at the geostationary satellites, and that will be it. So in terms of satellites, they can be used for communication, so satellite phones, TV signals, for military users. You need to know a few of these bits, so like military can use it to locate criminal or whatever. For scientific research, so to be able to look at pollution on Earth, or what goes on with the universe further outwards. So not just looking at the Earth, but also studying the universe. They use them for weather and climate, so to predict and monitor the weather, and global positioning. There are a lot of different types of orbits. So you have the polar orbits, you have low Earth orbits, and then you have equatorial orbits. The important part is that we can, depending on where we place so from this equation, we know that wherever we place the satellite, its period will depend on how far it is. So for example, the further I place a satellite, the longer it will take for it to spin around the Earth. The closer a satellite is to the Earth's surface, then the shorter the period. It will cover the Earth much quicker. It will go around the Earth much quicker. So it will provide you with more opportunities to, within 24 hours, let's say, that the Earth takes to spin around its own axis, it is possible to provide you with much more detail if the orbital period is lower, since it's closer to the Earth. Now, geostationary satellites are placed in a very specific orbit, the geostationary orbit. That is directly above the Earth's equator. And it rotates in the same direction as the Earth rotates, and it has an orbital period of 24 hours. So it stays in a specific location fixed above the equator. So this is the equator. A satellite will be fixed directly at that spot. I'm not really good at drawing satellites, so imagine this is a satellite. looks like a bow. But yeah, it will rotate in the same direction. And it has an orbital period of 24 hours. Now, the useful thing about geostationary satellites is that they remain in the same place. They're very good at being used for telecommunications, so like transmitting and receiving signals for television broadcasting. And for that to be able to work, a TV satellite dish has to be pointing in a fixed direction. So this type of satellites, geostationary satellites, allow, since the spin and the stay at the same point as the spinning at the same time as the Earth is spinning, it means that they stay in that same position and they spin around with the Earth. So the satellite dish, a TV satellite dish, will need to point at that fixed direction, otherwise you don't get signal. So there are thousands of them being used at the same time, and they remain in the fixed positions around the Earth. We can use Kepler's third law to figure out how far they need to be, since we already know that their orbital period is 24 hours. And in seconds, this needs to be 24 hours times 60 times 60. And we can use this relationship t squared is equal to 4 pi squared over gm r cubed to figure out how the satellite needs to be from the surface of the Earth in order for it to have 24 hours orbital period. I hope that makes sense. This is the end of, well, not the end of the whole chapter, but of the Kepler's laws and their applications and how it links to circular motion. If you do have any questions, please do write them down and let me know. See you for the next lesson.